formation, enzyme substrate, enzyme interact with the substrates with some kind of in enzyme part, few amino acids, few hotspots we can say. Hotspots are few amino acid or residues, amino acid residues interact with the substrate, and then that interaction makes the substrate into a product. Okay, so that few hotspots join together and it forms as an active site. So in enzymatic reaction we call as active site. In an enzyme you can see, you can find more than one active site. Okay, so this active site is the one that particularly interact with the substrate, not remaining protein powder, remaining protein portion of the enzyme may not interact. Okay, only the portion which forms as active site will interact with the substrate molecule. Okay, so here you can see this is a protein structure, primary protein structure. You can see primary protein structure, amino acids join together to form a protein, isn't it? So these amino acids, on these amino acids, those formed in active sites may present on different position. Okay, once the protein folded into three-dimensional fold with the different bondings like anionic bonds, sulfide bonds, and other interactions, it forms as all these come together and forms as a binding product, binding site. So this binding site we can call as active site of that protein. So here you can see in this protein, these are the amino acids of active sites. It forms bond with the substrate molecule. So you can see the substrate enzyme complex is formed here in the panel. Okay, so once it is formed the enzyme substrate panel, so these amino acids exchange their bonds. Okay, exchange their bonds and then form complex, and then they interact with this substrate, and substrate interact with the enzyme amino acids, and this substrate eventually convert into other molecule that we call as product. Okay, so here you can see representation, enzymatic representation, enzyme and substrate molecule. It forms as an enzyme and substrate complex, and you can see after some time, so enzyme will interact with the substrate molecule and it convert into another molecule or another product. So that we call as a product. Okay, so enzyme will again come back to its original round, so original position, and may, if the substrate is there, it may interact with the substrate and form enzyme substrate complex, and again it will go like cycle. Okay, so in this process enzyme will not be consumed. Okay, that is main thing. Enzyme will not be consumed, and only substrate will change its orientation, change its character from substrate to product. Okay, so here you can see the enzyme active site. If you disturb the enzyme whole part, if you make any changes of this structure, so that changes may eventually change the active site structure also. Okay, so if active site changes its structure, if the protein, the protein may not interact with the substrate. So if it changes its structure, the protein will not interact with substrate, and then it will not perform any activity. So you will not find any enzyme and substrate activity. So substrate will not convert into a product. So this kind of action, this kind of effect we can call as negative effect, or you can call as loss of activity. So there are several proposals were proposed how enzyme interact with the substrate. Okay, how enzyme will interact, how enzyme will recognize its own substrate molecule. Even though many substrates are available in this reaction, in this mixture, how this enzyme will go and interact only with its substrate molecule. So there are several proposals. In these proposals, two proposals were become famous. First, key lock and key model. You know this one. Lock and key is in this model, the enzyme active site will be a kind of form as a shape, or it will be a rigid shape. Okay, so that will not change that will not change. Okay, so if substrate has the same model, same shape, then only it will bind. Okay, then only it will bind to that active site. Okay, so that they call it is called as lock and key model. So you can see, you if you have 1,000 locks, if you have only the key which is entering into that uh, keyhole, that only will open that locks. Okay, if you have 1,000 lock keys also, it will not work. Only one key will open the lock. Okay, so this model was proposed in 1894 by Emil Fischer, and he suggested that this active binding site will have a rigid structure. So whatever the substrate bind, which is having the complementary shape, that only enter into this active site and will interact with the active site and acids and become into a product. So this was believed for several years, because that explained exactly how the structure of substrate, once the structure of substrate is identified. Okay, so later process. So here you can see, this is active site and substrate. If it is having the same orientation, same binding site, binding structure, same orientation, then only it will interact with the active site. So here also, here you can see the substrate molecule. So carbon, hydrogen, sulfur, whatever molecule they have their own shape. Once the active site shape is complemented to this substrate shape, then only the substrate goes and interact with the active site. Okay, so this was explained nicely, and many years it was believed same thing. The same active site and active site of the structure and the substrate site will go together, then only they will bind and form as a complex we call as enzyme substrate complex, and then later stage it will turn into a product. Okay. So later, people thought that okay, that is fine. Proteins are biological molecules and soluble molecules. So how this only site will be having rigid structure? Okay, so if it is a rigid structure, how proteins will have, we know how they are folding with the rigid nature, with the rigid structures in it. Okay, so later many people were thought it may be different. Okay, later in 1958, after 100 years, Donald Coastland suggested that this lock and key model may not be present in biological system, because these proteins are biological molecules and soluble in water, having soluble nature. So rigid molecule will not get into soluble. Okay, so they may have some kind of modifications during the substrate interaction. So that he proposed that induced lipid model. So when the substrate having same binding complementary site, so when the protein approaches it, okay, so the protein active site form complementary structure, or the complementary structure of the protein may changes in its active site. This interaction or substrate interaction may induce some changes in its active site. So this proposal says that induced lipid model. So here you can see how nicely he explained. This is a protein. So protein active sites, amino acids are there after three-dimensional structure at one site, one place. So we call as pocket, or we call as cleft, we call as active site. Okay. So once the substrate approaches to this active site, so if this enzyme interact with this substrate molecule, so enzyme make some changes, or enzyme induce the changes in its structure to bind complementary tightly with the substrate molecule. So once the enzyme interact with the substrate, so it changes its structure and makes a tight interaction with the substrate molecule by inducing changes in its active site. Okay. So in due course, the enzyme interact with the substrate interact with the enzyme, and substrate become into a product. Okay. So this induced lipid model accepted by all people, because this may be the reason how proteins interact with the substrate molecule in biological system. Okay. So now, is it clear? Is it okay?
Hello.
Hello?
Am I audible, sir?
Yeah,
Yes, sir.
you are audible because when I present this presentation, I cannot see you. So if you have something, please just you need to speak.
Yes, sir. Sir, in the last slide, sir, I have a doubt.
Yes,
Sir,
this is the one.
yes, sir. Sir,
Yes.
yes, sir. Yes, sir. So the enzyme will bind with the substrate only active site residue or with the whole?
No, engine interact with the substrate with active site only, not whole. That is confirmed. Okay, that is what whole engine will not interact with the substrate. Okay, so here you can see whole engine and active site molecules are very close. Okay, so this very close means once the engine form three-dimensional structure. Okay, so this structure it is in three-dimensional. Okay, so that is what we can call as native engine. When it is not denatured, it is called as native engine. So when it is in native form, so all active site binding in residues come together or close together. Okay, so that site, that portion we call as active site.
Then, sir, how substrate identify the active site residue of enzyme?
Yeah, so when these enzymes interact or substrate interact with this active sites, so active sites again move together, closer together, and then they changes its active site structure according to the substrate shape. Okay, so that
Okay, so based on the
yeah,
shape enzymes bind,
yes,
right?
yeah, yeah. That's what
Okay.
I'm saying. Engine, say for example, it is opened it is like opened molecule. Okay, these you can see the fingers. These fingers are the what is that active site residues. Okay, so when the substrate is come, these active site residues come closer and interact with the substrate. Maybe okay. So this changes we call as induced lipid model. So when substrate bind to this active site residues, this residues changes its structure very complementary to the substrate molecule. Okay, not
Okay, sir.
a whole part is not interacting here. Only active site residues only interact with the substrate molecule. Okay,
Got it, sir. Got it. Thank you, sir.
so now now this model is accepted by all enzymatology scientists, and they are they use this model to explain the enzyme how enzyme interact with the substrate. Okay, so now as we know, these enzyme molecules are the acts as a biocatalyst, and then they will not consume in the enzymatic activity. And another important property, another important character is they reduce the activation energy. Okay, so by reducing activation energy and by for acting as biomolecule, what is that catalyst? Acting as biocatalyst, they will increase the activity of the reaction. Okay, so how these enzymes increase the rate of the reaction? How they will enhance the rate of the reaction? You can see any reaction. So, for example, they will to convert into product. Okay, so it has to has some force to start the reaction. Okay, so that force we call as energy. Okay, so once the force is activate this molecule to convert into a kind of activated molecule, and then this activated molecule slowly convert into a product. So So once you can see the molecules get activated, so in this getting activated, some energy you are providing for that. Okay, so once the activated molecules turning to substrate, so the energy will lose and the activated molecules convert into a product. Okay, so here the important thing is activation energy is needed to start any chemical reaction. Okay, so by like that only all chemical reactions will start. So if you see blue graph and red graph, okay, so the blue graph is the one it started required uncatalyzed reaction. There is no catalysis is involved here. Only it started its own reaction. Like energy, you have provided the energy, and then that activation energy activated that molecule, and that molecule activated, and that molecule converts into a product. Okay, so if you add any catalyst in this reaction, that catalyst trigger the activation, enhance the rate of the reaction, and then it reduces the utilization of the energy. Okay, so here you can see the red mark, red graph, where the catalysis is involved. So it reduces the activation energy consumption. So here you can see delta G. There is no difference between free energy between catalyzed and uncatalyzed reaction. Okay. So here from whatever the loss of energy, free energy is same in catalysis and uncatalyzed reaction, whereas the activation energy is differ here. Activation energy is required in uncatalyzed reaction. The activation energy is minimized, reduced in the catalysis, where catalysis is involved in the reaction. Okay, so enzymes increase the reaction rate by decreasing the amount of energy required to form a complex of reactants that is competent to produce reaction products. Okay, this complex is known as the activated state or transition state complex. Okay, so as I said, the molecule get need activation energy. So once the molecule become activated, and it is called as transition state complex. Okay, so that transition state complex, when molecule enter into the transition state complex, the molecule will turn into a product here. Okay, before that, before it become transition state, it requires some kind of energy. Okay, so that we need to provide. Okay, enzymes and other catalysts accelerate the reactions by lowering the energy of the transition state. We have seen in the previous graphical representation how uncatalyzed reaction require large amount of energy to activate the molecule to turn into transition state or transition state complex or activated state molecule. When you add a catalyst or any enzyme, if you add enzyme here as a catalyst, because enzymes are biocatalysts, okay, so that will lower the required energy here to become activation state, transition state. So the energies of the state of chemical reaction, you can see uncatalyzed dash line, a substrate needed lots of activation energy, okay, to reach the transition state, which then decay into lower energy product compounds. Okay, so when enzyme catalyzed, if you add enzyme to this one, a solid line, so energy binds to substrate, then stabilize the transition state, and to reduce the activation energy required, produced product were finally released. So here you can see transition state, increasing transition state when you don't have the substrate, and when you add the enzyme, it will form as an enzyme substrate complex, and it reduces the activation energy requirement, and it will form a product where lower energy molecules will be formed here, and substrate product molecules will be released out of the released from the enzyme, and enzyme again and again join to new cycle reaction. So this is explained enzyme and substrate. Enzyme substrate complex is formed. Enzyme substrate complex converts into enzyme product complex, and enzyme releases the product molecule. So all these reactions can be done either this side or that side, reversible reactions. Okay. So once enzyme substrate is formed, if energy or enzyme is not in good active sites, it may come back to energy and substrate molecule. Okay. So once enzyme substrate convert into enzyme product, so product will later it will release from the enzyme, and the enzyme again enter into new cycle. Okay. So here many chemical energies we have to discuss about how these can be calculated. You might know these chemical reactions in your chemistry, so I'm just skipping some of this. And in these chemical reactions, there are two types of chemical reactions in our chemistry. One, it is called as exothermic reactions, another one is called as endothermic reactions. Exothermic reactions where the enthalpy changes has a negative value, where you can see energy will be released. Okay, so here different reactions you can see, general chemical reactions, reactions between potassium permanganate and glycerol, or reaction between sodium and chloride to make sodium chloride. Okay, reaction between water and any strong acid. Okay, and reaction between water and any hydrous salt, dissolving laundry detergent in water. So these are all the reactions. You can see heat is generated in these reactions. Okay, exothermic reactions. In these exothermic reactions, the enthalpy is in minus values. Okay, so just a good example, if you take a small laundry detergent in your hand, pour some water and rub little bit, you can feel kind of heat in your palm, on your palm. Okay, so these are the exothermic reactions. So most of the biological reactions where energy is released, where ATP molecules are formed during this reaction, energy is released, and this energy will be used to make what we call energy rich molecule. Okay, those are called as energy rich molecules, ATP molecules. Okay, so the energy will be released in this chemical reaction. That energy will be coupled to synthesis of energy rich molecule. Okay, and some reactions, endothermic reactions, where the energy is required to process that reaction. Okay, so like in biological reactions, cleavage of ATP molecule, ADP to inorganic phosphate, where this energy will be released, and that energy will be utilized to other reactions. Those are all called as coupled reactions. So reactions where ATP high energy molecules are cleaved, and then that energy will be utilized in the main reaction to process that reaction. Okay, so we are going to see many reactions here in biological system where ATP molecules are utilized to make the reaction, and where ATP molecules are synthesized when it is broken, bond is broken, when energy is released. Okay, so this reaction, what we are talking, endothermic reactions, in these reactions, enthalpy is positive value. Okay, so when it is positive value, we have to put the energy here, activation energy, or it will take the energy from the surrounding molecules and process the reaction to complete. Okay, so you can see many examples like photosynthesis is good example, and cooking egg and ammonium chloride is dissolved in water, endothermic reaction takes place. Okay, so here, many biological reactions are follow these endothermic and exothermic reactions to require to complete the reaction process. Okay, so the rate of reaction is entirely depending on two different parameters. One is called as transition state, what we have seen in previous graphical representation, where the enzyme interacts with the substrate molecule, and substrate molecule forms as a substrate enzyme substrate complex. So that in forming as a enzyme substrate complex is a transition state. So this transition state is depend on the what is that the energy, what kind of energy we are providing to interact with the substrate molecule. Okay, so an unstable activated state, transition state is an unstable activated state in which new bonds are formed and old bonds are broken. Okay, so that we call as activated state or transition state. Okay, the difference in energy levels of substrate or product, and the transition state, that is like the rate of reaction reflect the activation energy. At the top, the energy K is point at which decay to substrate or product is equally probable. So that's what I told you. Enzyme substrate complex, when it is enzyme substrate complex is formed, it depend on the kind of there is equal probabilities. It may turn back to enzyme substrate or it may turn back forward to enzyme product. Okay, the middle state we call as transition state or activation state. So this transition state may going forward to form as product or turn back to form as substrate, depend on the energy what we have or catalysis what involved in the reaction. Okay, so if you raise the energy, means if you put the more energy, that will move forward to give the product. If you add the catalyst also, that will move that will make the forward reaction to make the product molecule. Okay, so this I'm just skipping to see first order, second order reactions in your chemical reactions. So just go through with that. Okay, and now those are chemical reactions. Just you see your chemistry book one more time, you will understand. Okay, so now when you come to biological enzymatic activity, so enzyme activity can be represented by different units. Okay, so the enzyme amount of enzyme which convert into amount of the substrate into product. So different units are people are using here. Okay, so enzyme activity, it is defined as the amount of enzyme that will convert a certain amount of substrate into product. So here we have to take a kind of kind of standard temperature, or what is constant temperature, constant conditions like temperature and pH. Okay, and time point also we need to consider. Okay, so the International Enzyme Commission has adopted a standard unit of enzyme activity called as international unit. So if you see any enzyme, many enzymes are commercially available nowadays. So if you see any enzyme bottle or label, that they will give as in international units, this much international units, like 20,000 international units, 100,000 international units, or 1,000 international units. Okay, so these international units define as the amount of enzyme that can convert 1 micromole of substrate into product per minute at 25 degrees. Okay, so that define whatever enzyme that define the amount of enzyme that convert 1 micromole of substrate into product per minute in that temperature, constant temperature that may be 25 degrees. Okay, so some people, some research people, they use this enzymatic activity in ketones. Okay, so here we international units they use per minute, whereas when you see many reactions after within seconds. Okay, if you wait for a minute, before that some reactions will complete. Okay, so to capture their reactions also, people use another way to express their activity. It is defined as the number of moles of substrates transformed, converted into product in seconds. In second, okay, at 25 degrees. Okay, so those are all, those engines will have very fast active rate. Okay, these engines express in the form of ketones. Okay, ketones can be used all type of engines, but it expresses in seconds. Okay, we need to keep that in mind. Okay, not only that, people use in specific activity. Okay, so people use specific activity. Most of the engine purification labs, all engine purification labs, they use in terms of specific activity to express this purity of that engine or activity of that engine. Okay, so specific activity is, it is defined as the number of engine units per milligram of protein. So they use the how much protein used in this reaction. Okay, that will express, that will give the specificity of that particular protein. If you do the purification process, you will come to know at the end of the purification process, you can see what is the starting point of the enzyme specific activity, and at the end what is the enzyme specific activity. So in this process, enzyme specific activity in purification, it will be increased. So in beginning steps, improved enzyme, several improved enzyme means, when you have the cell or when you have the tissue, when you lysate that one, so in this lysate, that is called as crude enzyme. Okay, that whole complex we can call as crude enzyme. So in this crude enzyme, you will have different molecules. Nucleic acids will be there, and lipids will be there, carbohydrates will be there, and other kind of complex molecules will be there in this enzyme complex, that crude enzyme. So when you take that crude enzyme, say for example, you are taking 10 microliter. So here how much volume you are taking is not important. So you have to calculate how much protein is there in this 10 microliter. So that's why they use the milligram of protein per milligram of protein in the specific activity. So when you take the crude enzyme, lots of proteins will be there. You will have more protein value and less enzymatic value. Okay, so when you start purifying, when you're removing all these unwanted proteins, unwanted molecules from the mixture, only your protein will be there. So you will have less protein amount and more enzymatic amount. So that's why, as I said, in protein purification, when you reach the end point, you will have more enzymatic activity than you have protein content in the volume. That's why they use the specific activity per milligram of protein. Okay, so not only that, people use different ways, as I said, ketones, international units, and also turnover number. Okay, turnover number can be used in two ways. One way, it is redefined as the number of moles of substrate transformed per minute per mole of enzyme, unit per mole of activated state or catalyzer center under optimum conditions. And turnover number, you can see, this tells how many substrate molecules are converted into product by each enzyme molecule. It tells us how fast enzyme work or turn over the substrate into product. So for example, you can see for catalysis, for catalase, turnover number is 5 into 10 to the power of 6. Okay, whereas alpha amylase is 1.9 into 10 to the power of 4. So This indicates catalase is 250 times more active than the amylase. So here you can see catalase enzyme is more active when you compare with the amylase, even though you take same concentration of protein as well as amount of the enzyme or amount of the enzyme number. So another way, turnover number, moles of substrate per minute, moles of enzyme moles of substrate is 0.5 into 10 to the power of 6. Moles of enzyme is molecular weight you need to calculate here. How much, it depends on the, how big the enzyme also. Okay, some, some small enzymes have more turnover number, when lot of enzymes have less turnover number. It is very natural. Okay. Okay. Any doubts here? That's all my class. That's all my class today. Hello.
Yes, sir.
Yes, sir. It's clear, sir.
Right. So any doubts? I finished my class. If you have a question, I'm happy to take.
No question, sir.
Alright. Okay then. See you tomorrow.
Yes,
Thank
sir.
you, sir.
Thank you, sir.